A fan is not cooling an EV charger by itself. Cooling comes from the complete path. Power modules transfer losses into heat sinks, air crosses those fins, a fan supplies the pressure, and an outlet releases the heated air without sending it back to the intake. One bypass can leave a critical module hot while total airflow still looks impressive. Start with the thermal budget. Document loss from the AC to DC and DC to DC power stages, bus bars, connectors, and control electronics. Then define the worst normal ambient, the allowable temperature of the most sensitive component, hotspot margin, and the charger's approved derating logic. Rated electrical power is not the same as cabinet heat loss. Use measured or validated loss data from the actual power architecture. For a first energy balance, required volumetric airflow is heat loss divided by air density, specific heat, and the permitted air temperature rise. This calculation is only a starting point, not a fan selection. Filters, louvers, heatsink fins, cable bundles, and outlet grills add pressure loss. The fan curve must intersect the cabinet system curve at the required airflow in both clean and loaded states. Free airflow from a catalog does not prove installed flow. Air direction matters as much as fan size. Bring the cleanest practical air into the cabinet, sweep every major heatsink, and exhaust it where hot air cannot return directly to the intake. Baffles or ducts may be needed to prevent a short loop around the fan. Check the whole cabinet, not one convenient temperature sensor. Architecture follows the pressure path and envelope. An axial fan can provide high flow in a direct path. A centrifugal blower can provide more pressure and routing flexibility. A long outlet package only makes sense when the geometry truly needs it. Compare each option at the same operating point, supply, control, temperature, and acoustic boundary. Open ventilation changes the enclosure boundary. A filter adds pressure loss and requires maintenance. Adding an opening or changing a filter can alter the system-level protection result, so use the charger's exact enclosure certification and installation manual. A robust control loop uses representative temperature sensors, a speed command, fan status or touch feedback, alarms, and safe power derating or shutdown. One convenient sensor cannot stand in for the cabinet's hottest component. N+1 is not just a fan count. Verify the cabinet with one fan failed, a dirty filter and high ambient together when that combined state is credible. The acceptable result is a controlled thermal map, not simply another spinning fan. Ambient temperature, altitude, dust, rain, salt, condensation, and solar load all change the thermal duty. Use the exact charger environment, component derating data, and certified operating limits instead of a generic cabinet rule. Treat filter loading as a predictable pressure rise event. Trend pressure, airflow, speed, hotspot temperature, and alarm history. Design pressure margin and service access before the filter blocks, not after. Qualification should cover rated power, ambient extremes, supply tolerance, dirty filters, blocked intake, fan failure, environmental boundaries, solar load, altitude, acoustics, and thermal recovery. For an OEM review, send heat loss, component limits, air path, pressure losses, ingress target, supply and control, redundancy and test conditions. Cabinet certification, electrical safety, and thermal event strategy remain system-level responsibilities.